The next convolutional based model we shall be working on is the MobileNet. Mobile nets are efficient convolutional neural networks for mobile vision applications, developed by Andrew Howard et al. Of Google. This is a class of efficient models called mobile nets for mobile and embedded vision applications. Mobile nets are based on a streamlined architecture that uses depth-wise separable convolutions to build lightweight deep neural networks. We introduce two simple global hyperparameters that efficiently trade off between latency and accuracy. These hyperparameters allow the model builder to choose the right size model for the application based on the constraint of the problem. Previously, we had seen the VGG, we had seen the inception net, we had seen the res nets. And we also saw that to increase the accuracy, it sufficed to stack up more layers or more convolution layers. But there is a problem with this method or with this way of approaching building convolutional neural networks. When we deploy deep learning models under certain circumstances or in environments like embedded systems or mobile phones where resources are limited, we can't just afford to keep on stacking up these layers just to increase accuracy. It's important for us to get a balance between increasing the accuracy and managing the resources properly. In this section, we first describe the core layers that MobileNet is built on, which are depth-wise separable filters. We then describe the mobile network structure and conclude with descriptions of the two model shrinking hyperparameters, the width multiplier and the resolution multiplier. So we start with the depth-wise separable convolution. So right here we have to the left the standard conv layer with batch norm and ReLU. To the right we have a depth-wise separable conv layer, which is made of a depth-wise layer, which is this, and then a point-wise layer, which is this 1x1 conv layer. So a point-wise layer is basically a 1x1 conv layer. And then to form the depth-wise separable, we join this depth-wise with a point-wise layer. So we could get back and see the depth-wise convolutions and then the point-wise convolutions, which are just 1x1 filters. Let's take a look at the depth-wise conv layers. Before looking at that, recall with a conv layer like this one and an input of df by df by m. So we have df width, df height, and then m different channels. We could obtain this output of df by n if we are sure that we have same pattern and that we have n filters right here. So with this, we are able to have this output. Now, with the depth-wise conv layer, unlike this typical conv layer, when we get one of these filters, so suppose we have this particular filter which is dimension dk by m. So the m here is because we have m different channels. So each of these will represent a patch for each of the channels. So when multiplying this filter with this input, we simply take this first, multiply with this first channel, the next with the second, and right up to the end with this last one. So that's how we obtain one of this dk by dk values. And then since we have n filters, we repeat this n times to have the rest of the n channels. So we had seen this already. But with this depth-wise conv layers, this is not the same. There is some modification in the way these filters are applied on the inputs. Now, you first notice that we don't have a channel or a depth dimension when it comes to these filters. We only have the height and the width. So right here we have dk by dk and there is no depth. And that's simply because with this, we do not multiply all through all these channels. So this one is responsible for multiplying just one channel. This other filter, the next channel, this other filter, the next channel, this other filter, the next channel, and so on and so forth. So we have m different filters. Notice here that we had n filters, but right here we have m filters. So instead of one of the filters, as it was in this case, multiplying through all the different channels, we have just this one filter multiplying one channel or applied on one channel, and then this on the next, and so on and so forth. Now, if this isn't very clear, let's suppose we have this 2-channel input. So we have this input, which is say df by 2. So we replace this m by 2 since we just have 2 of this. And then we have this conv layer, which is made of just 1 filter. So instead of n filters, we have just 1 filter. And this 1 filter is dk by 2, which is logical because we actually have 2 channels. So here we are working with dk by 2 channel kernel. Now, applying this kernel on this input, we have each of these kernels which is going to be applied per channel. So this one goes to this channel, the next one goes to this other channel, and then to get the output, we'll simply multiply these different values, multiply this once, add them up, and then get one of these outputs in the output we have here. So one of the positions will be occupied by just carrying out this operation. Then, depending on the stride, we shall move this patch to the next position. So we've seen this already, where we just take from here, we slide to the next position, slide, and so on and so forth, right up to the end. And with that, we can get all the different outputs, or all the different parts of our output. So we've seen how with this, we are able to get an output with just 1 channel, since we just have 1 filter. So our n equals 1 in this case. But for the depth-wise conv layer, where we have these 2 filters now, so we have m equals 2 filters, and each of the filters is a dk by dk. So it's dk by dk since it doesn't have a depth. So with this, we take one of these, we put here, one of these we place here, we multiply these values. But unlike with the usual conv layer, where we have this put in its positions, multiplied, and then added out to give the output, here once we multiply and we have our outputs, the final output is gotten by simply multiplying just one of these filters with the input, or with one of the channels of the inputs. So when we multiply, let's say this with this, we get the value in the output. Multiply this with this, we get its own value in the output separately. So these multiplications are separated with respect to their channels. So different channels have their different filters, and so different outputs with different channels too. So unlike here where we ended up with just 1 channel output, here we end up with a 2-channel output. So that's why we leave from m here to m, and from m here to n. And when n equals 1, like in this case, we have n equals 1. And here, since m is maintained, we leave from 2 channel to 2 channel. So that's a depth-wise conv layer. Now, we can study the number of operations we have depending on the layer we're working with. For the conv layer, since our output is df by df, we have, first of all, the df by df different positions we can find ourselves when doing these computations. So we have df by df times dk by dk, since our filter is dk by dk, by m. Now, since we multiply through all the channels, so we have dk by m, and then since we repeat this n times, we have times n. So that's how we have this number of operations. Now, for the depth-wise convolution, if you notice, we have this dk by dk, or we have this df by df, since we have df by df as output, and then we have dk by dk, since we have this dk by dk filters right here. We have times 1, since we don't have the depth, and then times m. So notice that there is already a gain in the number of operations when working with this depth-wise convolutions. And it's these calculations that the authors put forth in the papers, which showed how they had the tk by dk by m by n by df, and then the later on showed how for the depth-wise convolutions we have dk by m by df. So the n is taken off with the depth-wise convolutions. And then since the depth-wise separable is done by combining the depth-wise convolution with a point-wise convolution, which is this 1-by-1 filter convolution, we have to take the depth-wise convolution value which we had from here, which is this, and add it up to the 1-by-1 filter convolution. So that's how we obtain m by n by df, Anyway, this can be obtained simply from this previous formula, since it also represents a convolutional layer. So from this previous layer, or from this previous formula, if we consider dk to be equals 1, since we are dealing with a 1 by 1 filter, then we should have m by n by df by df. So right here we have m by n by df, since we've considered dk to be 1. Now we add this up and we have the number of operations for a depthwise separable convolution layer, which is a combination of the depthwise layer and then the pointwise layer. Now what we do is we're trying to find a relationship between these two operations, or these two number of operations. So in the numerator right here we have for the depthwise separable, and the denominator we have for the conv layer, and we obtain this result where we have 1 on n plus 1 on dk squared. This try to tell us that the more we increase n and the more we increase dk, the number of operations for the depthwise separable layer is small compared to that of the usual conv layer. And they say here that the MobileNet uses 3x3, that's 3x3 filters, depthwise separable convolutions, which uses between 8 to 9 times less computation than standard convolutions, at only a small reduction in accuracy, as seen in section 4. Now, as we've seen, the backbone of this depthwise, or this MobileNet, is the depthwise separable layer. And right here we have the conv layer, we have a conv dw, that's a depthwise separable layer, we have conv, we have depthwise separable, conv, depthwise separable. Up to this we have this repeated 5 times, we have depthwise separable, we have conv, depthwise separable, conv, average pool, fully connected, and then the softmax. So as we've discussed, the whole point of this MobileNet is to reduce the number of computations while maintaining a reasonable accuracy. Now, although the base MobileNet architecture is already small and low latency, many times a specific use case or application may require the model to be smaller and faster. And in order to construct these small and less computationally expensive models, we introduce a simple parameter alpha called the width multiplier. The role of the width multiplier alpha is to thin a network uniformly at each layer. So for a given layer and width multiplier alpha, the number of width, or the number of input channels m, becomes alpha m, and the number of output channels n becomes alpha n. And from this we can recalculate our formula by multiplying m, putting at alpha m, multiplying n, putting at alpha n. Now note that alpha lies between 0 and 1, so alpha isn't greater than 1. So basically, as we said, we're trying to reduce the amount of computation by the model. So doing this will reduce the value of m by alpha, and then alpha is typically set to values of 1. So 1 is a standard form, 0.75, 0.5, and 0.25. So it may happen that you have a certain mobile device or an embedded device whose capacity may be too small to withstand the computational resources needed when working with a depthwise separable layer with the standard value of alpha equals 1. So we may modify it to a value like, say, 0.5, such that the computational resources needed are reduced and then can fit that particular embedded device. So this is actually left to the engineer to tune this value of alpha to suit the needs of the particular application while taking note of the accuracy. And the width multiplier has the effect of reducing computational cost and the number of parameters quadratically by roughly alpha squared. And then for the resolution multiplier, that's reduced representation, the second hyperparameter, it reduces the computational cost of a neural network using this rho. So we apply this to the input image, and the internal representation of every layer is subsequently reduced by the same multiplier. In practice, we implicitly set rho by setting the input resolution. So our formula is modified this time around. Now, since our inputs come up with df, we now have row df. So instead of df we have row df, and instead of m we have alpha m, and instead of n we have alpha n. So right here we've simply modified this, and it has modified the number of operations needed when data passes through these layers. Now when this row is set between 0 and 1, which is typically the kind of values of row we choose, the input resolution of the network is generally taken to be 224, 192, 160, 128. But when row equals 1, which is the baseline mobile net, we had 224. So we just modified this value such that we obtain these other values. So this is kind of like the kind of values we have in practice. But depending on your problem, you may want to modify this. So it all depends on you and depends on the kind of problem you're trying to solve. And then we have some tables which show us how modifying this mobile nets and the different parameters affect accuracy. So we have this alpha equals 1 mobile net, which is giving us an accuracy of 70.6. When reduced to 0.5, we drop to 63.7. To 0.25, we drop to 50.6. And then the comparison done when working with only conf layers and when working with depth-wise, that's with the mobile net itself. So we'll see how this accuracy actually drops as we go to the usual or the standard mobile net, which is made of both depth-wise separable layers and conf layers. So we drop from 71.7 to 70.6. But we can notice that the number of parameters to greatly drop from 29.3 million to 4.2 million. So this is good enough for us to say we can let go of this 1.7% which has dropped, or which we would have had if we were working with a conf layer. Now the number of operations, as you can see, also drops considerably as we move from the conf mobile net to the mobile net itself. So let's build a simple mobile net. Before doing this, we have our custom layers. That's the custom depth-wise conf 2D and the custom conf 2D. This custom depth-wise conf 2D is made of the depth-wise separable layer, and then this is made of the conf layer we know already. With the depth-wise separable layer, we don't actually need to mention the number of filters, so we'll take this off. So we'll take that off, whereas here we mention the number of filters. And the reason we don't need to explicitly define the number of filters in our code is because the number of filters here, M, depends on the inputs right here. So if we have a depth of M, we should have M filters. And unlike the usual conf layers where this doesn't necessarily affect the number of filters, here we need not to multiply, or we need not to specify the number of filters. So with this, we now develop this depth-wise conf 2D layer with a batch num, and then we can go ahead to build our mobile net model. So we start with this custom conf 2D, we move to the depth-wise conf 2D, custom conf 2D, depth-wise conf 2D. We go through this 5 times. We have this right up to the output. Notice we have this parameter alpha. So we could define this such that we have an alpha right here. So we could take this, takes in alpha, and then we set self.alpha to be equals alpha. And by default, we could set alpha to be equals 1. So if we want to multiply alpha, if we want to change alpha, we could take a value like say 0.75. So that's it. Now, how does it modify our code? We notice first that for the custom conf 2D, since we want to work with alpha times n number of filters instead of just n filters, we see clearly here how the number of filters is multiplied by alpha. And then for the depth-wise conf layer, we have this depth multiplier, which is how we move from M to alpha M. Now this is for the custom depth conf, so we need to modify it right here. So doing this, we have this depth multiplier, which takes the value of alpha. So we'll modify this here, depth multiplier, and that's it. So with this, we have our depth multiplier, which gets the value of alpha we input. It should be noted that other versions of the MobileNet exist.